So, if you recall the topics that we have discussed during our last few lectures, we have talked about the various constructs of the Verilog language. We had looked at some of the fundamental constructs, the operators, how we can frame the expressions for evaluation, and some of the operations we have defined for assignment, for example, using the assign statement. There are a few more which we will be discussing in the due course of the lectures, but what we are trying to deal with in the present lecture is we shall take an example, and with the help of an example we shall try to illustrate a few points and concepts which are considered to be good design practice when someone is going about designing a digital system using a hardware description language. So, the topic of our lecture is Verilog modeling examples. Now, actually what we are trying to do here, let me try to explain this first. You have seen that when we model some system using Verilog, broadly there are two fundamental ways of doing it. So, we call it behavioral and structural. Modeling you can do either using behavioral or using structural. Now, in the example that I shall be giving in this lecture, we shall be just elaborating on this further. Now, just to tell you about when we talk about behavioral modeling, what we are actually doing? We are actually saying that how a system is working. We are not telling or talking about how it is actually constructed or is to be constructed. We are saying that, for example, I have an adder, the sum output should be A XOR B XOR C, the carry output should be A B or B C or C A. So, I am not telling that whether you will be using AND gate, OR gate, NOT gate or NAND gate or XOR gate what or how you will be interconnecting them. So, if I say just the behavior either in the form of this expression or in the form of a truth table, let us say that is a so called behavioral expression which is much easier to do. So, when you are a designer, when you have something in your head, in your mind, you are trying to design something. So, the first thing that you can write or start with is a behavioral description of your model or your thought process, what you are thinking about. Now, once you have thought about the behavior, now we can think about how we can implement it. Okay? Let us say, let us take that same example of a full adder. So, once we have thought about what is the functionality of a full adder, now you think about how you want to implement it. Now, you may see that well, I want to implement it using a technology where you have only NAND gates. So, let us not use AND or NOT operation. So, all the AND or NOT whatever is there, we will be translating them using De Morgan's law, using NAND operations only, and we will be implementing it using NAND. So, just in this diagram, so as I said, behavioral description is often the starting point, because it is easier to write a Verilog module in the behavioral model. But structural description, this is more with respect to hardware implementation. Like here I can say that well, to implement the carry output of the full adder, let us say to implement carry, I need I will say that I will need 4 NAND gates, let us say. So, and I will also tell how the NAND gates are interconnected. I will say that well, you interconnect the NAND gates like this. There will be 3 2 input NAND gates and 1 3 input NAND gate. This will be A B, B C and C A, and this will be your final carry output. So, this is what is your structural representation. You specify some modules and you also tell how they are interconnected. Now, obviously, this is much more detailed. So, when you are thinking of the behavior, you have not yet thought about these gates and how they are interconnected. Okay? So, there will be a process that you will have to go through, that from behavioral to structural you will have to make a translation, right. So, the normal design process is that we start with a behavioral description. Now, in our behavioral description, our total description may consist of one or maybe multiple modules. Let us say one. We systematically try to convert them into structural descriptions. There can be several steps. I shall take one example and I will show you that how we can use several steps in the translation and how you can carry out some kind of a hierarchical design process in order to achieve it, at the end of which you will be having a number of modules, all of which are specified in a structural description. So, you have a total design which is a structural description of a system you want to build. So, from behavioral to structural, this is normally the step which many people follow. Okay. So, we shall be taking the example of a 16:1 multiplexer and illustrate some of the points I have just discussed with respect to this. 16:1 multiplexer, you know what a 16:1 multiplexer is. So, a multiplexer has a number of input lines, a single output line and a number of select lines. So, when I say a 16:1 multiplexer, so there will be 16 input lines, there will be one output line, and to select one of the input lines there will be 4 select lines. So, the rule is number of select lines is given by log to the base 2 of the number of input lines. Here input lines is 16. So, log to the base of 16 will be 4, right. So, we are trying to design such a multiplexer. So, to start with, we shall be giving the behavior. So, I am just showing you in this list that how we shall be proceeding with our design. So, in the first step, we shall be using pure behavioral modeling, which we shall see will be rather simple. Specifying the behavior of a 16:1 multiplexer is very easy. Then we shall be implementing the 16:1 multiplexer using several 4:1 multiplexers. So, we will be using structural description of the 16:1 mux using 4:1 multiplexers, but the 4:1 multiplexers will still specify using behavioral model. Then we shall be implementing the 4:1 mux using 2:1 mux, and we will be using still behavioral model of 2:1 mux. And finally, we will be specifying this 2:1 mux also in the structural gate level form, so that we have a complete hierarchical structural description. So, let us see. So, as we proceed with this example, these steps will be clear. So, we start with pure behavioral modeling, very simple. This is the complete Verilog module for a 16:1 mux. You see, for a multiplexer, as I said, there are 3 parameters. This in and cell are the input lines and the select lines. So, in is 16 bits, select lines is 4 bits and out is a single bit output. So, you can specify the behavior of the multiplexer using the single statement, out equal to in within square bracket cell. You see here, as if we are accessing one element of an array, the input lines, there are 16 of them. You imagine the input in as consisting of a 16 bit array, where the index values will be 0, 1, 2 up to 15, and the select lines that you are using 4 bit select line. So, in 4 bits what will be the values? The value can range from 0 up to 15. So, if I can use the select line as the index of the array, so I will be selecting that particular element and I will be sending it to the output. That is what a multiplexer does. Okay. So, you see here we have selected a particular bit of this input vector in which bit? The bit specified by cell, and that particular bit we are storing in out. This is your multiplexer. So, let us start with this. We have done a behavioral modeling of this multiplexer. Okay. Now, how do we test it, whether it is working correctly or not? We write a test bench. Just go back, we have a module like this mux 16:1, where there are 3 parameters input, select and output. Okay. And now, just we want to verify its operation through simulation, and we have written a test bench for it. So, what is our test bench looking like? Let us say here we have instantiated our multiplexer mux 16:1. You see this was mux 16:1. The parameter names are in, cell and out. So, we are using this notation to specify the parameters dot in, dot cell, dot out, and in this module the corresponding variables are A, S and F. And in order to express the data types, we specify A and S as reg, because they will be appearing on the left hand side, they have to be of type reg, and F is of type wire. This A is 16 bit, S is 4 bit. So, the test bench what I am doing, you recall, we will be just looking more formally into the constructs of a test bench later, but let us illustrate with examples. This initial block I am repeating, this means that we execute this begin end block only once. That is the purpose of the test bench. You will be testing your module once, whatever you have specified, those values will be applying to the inputs and you will see what the outputs are coming. Okay. That is the purpose of the test bench. So, just ignore the first 2 lines once more, we will again come back and explain this once more. Well, this line monitor. Monitor, we are monitoring a few of the variables. $time is a system variable that indicates the simulation time, and then in a C-like notation we are saying that we want to print the values of A, S and F. H is a hexadecimal specifier, because A is a 16 bit number, I specify percentage %H, S is also a 4 bit number percentage %H, and F is a single bit, I give it B, B means binary. Monitor means whenever any of the variables A, S or F changes, then only you print. You do not print at every time 1, 2, 3, 4, do not continuously go on printing. So, whenever there is a change, then only you print. That is the purpose of this monitor statement. Now, I specify the inputs. So, what I am saying is that at time 5, I apply hexadecimal value 16 bit hexadecimal H 3F0A. So, let us write down here also 3F0A. What does 3F0A mean? Let us write it down. 3 means 0011, F is 1111, 0 is 0000, A is 1010. these 16 bits. Now, if you talk about the index values 3F 0A, so index values will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. These will be the index values. So, if you think of a multiplexer, so these the input this 3F 0A you are applying here and you are applying the select line and you are getting the output F here, right. So, select line will be selecting one of these bits and that bit will come out, right. Now, at time 5 we are selecting what 0, we are applying all 0 to S. So, let us see what will happen. So, if we apply select line as 0, which means this 0 will be selected. So, what we will be getting? We will be getting this 0 as the output, right, and this will happen at time 5, right, at time 5. Next, in the test bench what we do? Well, we wait for another time 5, after a delay of 5 again we set S to 1, 4 hexadecimal, value is 1. So, now S is becoming 1. So, what will be the value? 1. Now, the bit is this 1. So, this 1 will be now outputted and this will happen at time 10, because we are having another delay of 5. Okay. You next look at, you have another delay of 5, now you apply S equal to 6. So, what is your 6? S is 6, 6 is here. So, this is 0. So, you will be getting this value 0. Now, this will happen at time 15 and the last one you apply S equal to C, C means 12, 1100, right, in hexadecimal. S equal to C, C means 12, 12 means you here, this is 1, this will happen at time 20, right, and at the end you finish, after another time 5 you finish the simulation. So, means if I create these two files, and I told you earlier that you can use any of the simulators to simulate these, and I had suggested to use the IVeryLog one, which is very easy and it is freely available. So, here in the examples that I am showing, I have used IVeryLog and GTK Wave to show you the simulation outputs. Okay. So, if I just simulate it using IVeryLog, so I get an output as is shown in the window here, this blue box. See exactly what I have shown here, the same thing is happening. See, at time 5 0 is coming, at time 10 1 is coming, at time 15 0 is coming, at time 20 1 is coming. You see, the first value that is printed in the monitor is time. At value 5 output is 0, 10 output is 1, 15 output is 0, 20 output is 1. So, I have also printed the values of A and S for your reference, A and also S. Now, initially at time 0 when the simulation starts, so the A is not initialized, S is not initialized, F is not initialized. So, all of them are showing X, right. Okay. So, you see, just from the behavioral specification you can do a simulation and you can get the simulation result like this. Now, the first two lines in the initial statement, I am repeating this, I mentioned this earlier also. See, these variations with time, this information you can also dump into a file VCD. Okay. So, here I am giving a name mux 16 to 1 VCD value change dump file. They will all be dumped in the file and I can specify which variables I want to dump. Well, 0 comma followed by the name of this module means that all the variables in this module and all the variables which are instantiated inside those modules, everything will be dumped. Okay, we shall see that what are the other options later in dump vats, but here we are dumping all the variables. Now, you can ask that, well, I can see all the simulation output like this, why do I need to use this dump file and dump vats? The thing is that, well, seeing the simulation output in a tabular form or just on the screen is not good enough in the form for text. Well, means often for digital circuits we want to look at the timing diagrams, how the values are changing at what times and so on. So, there is a tool I mentioned about GTK Wave. You can use the GTK Wave tool to view this file, and since I have dumped it with a name, you can just give a name GTK Wave, this particular file name, and it will show you a simulation result in the form of waveform like this. So, you see the font size is a little small, but you can decode. See, on top the time is mentioned. Just going back, at time 5 the values are starting to change, right. So, you see this is 7, this is 14, 21. So, 5 is here, this is our in, select and out. So, in was initially xxxx, select was out, select was x, out was also x. So, it starts getting selected here 3f0a, this is the value you have applied, select initially you have applied 0. So, the output you are getting 0 level, then select you have given 1. So, output has become 1, then select you have given 6, output has again become 0, then you have given C, output is become 1. So, exactly what you have seen here in the tabular form, the same thing is being shown here in a graphical form in the form of a waveform. Okay. So, it is sometimes much easier to view it on a waveform if it is a quite a complex circuit and the signals are means more complex and interacting. Now, the thing is that I have shown a very simple behavioral description of a multiplexer 16:1. I have shown how to write a test bench and I have shown you the simulation results. Now, what I will do, I will proceed with our so called hierarchical refinement. We shall be modifying our module description, but we shall be keeping our test bench the same. We shall not be touching our test bench. We shall be making modifications. We shall be again running the same test bench and verify whether the simulation results that we are getting is exactly the same as what we got here. That should be so, because it should, the result should conform to a 16:1 mux only. This we should verify at every step. Okay? Fine. So, we come with the version 2 now. Now, what you do, see, in version 1 we did something like this, we had a mux 16:1. Now, here what we are doing, this is our mux 16:1 description. So, here before explaining this, let me show you this diagram. We are implementing a 16:1 multiplexer by using 5 4:1 multiplexers. So, in the first level there are 4 of them. So, the 16 input lines are broken up into 4 each, 0 to 3, 4 to 7, 8 to 11, 12 to 15, and in the second level the output of these multiplexers are feeding the input of this. And among the 4 select lines, the least significant 2 select lines are applied here in these levels, cell 0 and cell 1, and the high order bits are applied here. So, this is how we built a 16:1 mux using 4:1 mux. This is a standard design, I am not explaining this, okay? These are available in textbooks. Now, actually in the description that I will show, we shall be instantiating the 4:1 mux 5 times, okay, with the interconnections like this. The intermediate lines are T0, T1, T2, T3. Okay. You see, we have done exactly that. So, this is the mux 16:1 description, input, output, and we have defined this wire T, T0, T1, T2, T3. So, these 5 multiplexers we have instantiated. Just check for M0 we have in 320 and select 120, output is T0. Let us see, for M0 input is in 320, in select our cell 0 and cell 1 and output is T0. Okay. Same thing, similarly M1, M2, M3 and finally M4, the input is T, you see input is T, T0, T1, T2, T3, you can simply write T, it is a vector. The high order bits of cell 3 and 2 are the select lines and out. So, this is a structural representation of this 16 to 1 mux in terms of 4 to 1 mux, but this 4 to 1 mux I am still describing in a behavioral fashion. 320 same statement 4 to 1 mux. So, this you can check, I am not showing the waveform. If you modify your design like this and if you run your simulation, you will be getting the same simulation output, same behavior as you have seen earlier for a full behavioral description of a 16 to 1 mux. Okay. So, this is our version 2 which can be checked to work in the same way. Next, we proceed one step further. Here we have used 4 to 1 muxes, right. Here we have used 4 to 1 muxes and our 4 to 1 mux was behavioral. Now, we are refining the definition of 4 to 1 mux. We are implementing a 4 to 1 mux using 2 to 1 muxes like this. Using 3 2 to 1 multiplexers, we can implement a 4 to 1 multiplexer. So, 2 and 2 inputs get here, the least significant select line will be here, most significant select line will be here. So, that way same way mux 4 to 1 I can use by instantiating 3 copies of mux 2 to 1. This correspondences you can check, but again this mux 2 to 1 I am still defining in a behavioral fashion. 2 to 1 mux I have just defined it like this, where select is a 1 bit and input is 2 bits. Okay. So, I proceed like this. So, at the last step I have the smallest multiplexer left with me 2 to 1, this I can straight away implement it using structural fashion. So, a multiplexer how do you implement a 2 to 1 mux? There are 2 inputs, one input and a select line. Let us say the inputs are in 0 and in 1, this is cell and the output is out. So, the way you can implement it is like this, you can take 2 AND gates and an OR gate, this in 0 can be connected here, this in 1 can be connected here and this cell you can connect directly here and through an inverter here. So, when select is 0, this will be 1, this in 0 will come out, and when cell is 1, this will be 0 and this will be 1, this in 1 will be selected, in 1 will be coming out, right. So, these are 4 gates. So, we specify this structural description for the multiplexer. This is what we have described here, a NOT gate, 2 AND gates and a OR gate. So, whatever we have shown here is the typical design flow of a designer. So, when a designer goes about designing a complex digital system, well, I have shown a relatively very simple example, so that you can appreciate just a multiplexer. I have shown that we start with using a behavioral description, then step by step hierarchically we break it up into structural representation at various levels, and when we are done we have all the hierarchical descriptions all described in the structural level, and what we have, the overall design is a complete structural design. Okay. So, I strongly recommend that you should try out these examples yourself, run them on a simulator, view the waveforms on GTK Wave or any other tool that you have access to, and you get a feel of the simulation and the feel of the design. Okay. So, we shall be continuing with some more examples in our next lectures again. Thank you.